There are three ways to prove two triangles similar: angle, angle, side, 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 and side, angle, side. On problem number 10, there's no angle information, so we're going to try side, side, side. We're going to take the smallest side of RQP and put it over the smallest side of MNO, the middle side over the middle, and the large over the large, and see if they equal the same ratio. And they all do in this case. They're all in the ratio 1 to 3, which you would call the scale factor. So triangle QRP is similar to triangle NOM by angle, angle. The order of the letters is important. When I said QRP, that path would be going down the smallest side, then across the largest. The same path has to be then NOM for the second triangle. In number 12, the triangles aren't similar. The angles are in the correct ratio. They equal each other. They both are in the ratio. The sides are both in the ratio, rather, of 4 over 5. But we don't have any information on the included angles. We have the 75s that are congruent at F and at J, but I've circled in green the angles that we needed. We needed to have angle E congruent to angle I, and then we would have had similarity by side, angle, side. But as they sit, we don't have the correct angles, so they are not similar. On number 14, the two triangles are actually congruent, which means they're the same size and shape, so they're similar, which only requires them being the same shape. And so triangle STU is similar to triangle XVW by side, angle, side. On number 16, the parallel lines give us some corresponding angles congruent. The angle at E and angle BDC are congruent. The angle at A and angle DBC are congruent, both by corresponding angles congruent. The third angles of the two triangles are angle C, congruent to itself by reflexive. So the two triangles are similar by angle, angle. They would be triangle EAC and triangle DBC. On 18, we're using the fact that we can prove the two triangles similar by angle, angle. It would be because the angles at A and C are congruent by alternate interior angles congruent due to the parallel lines. The angles at E and D are congruent for the same reason. The vertical angles at B are also congruent. So by angle, angle, we have two similar triangles. Now, in figuring what sides correspond, we could write the similarity statement, or we could simply say that corresponding sides have to be between the same pairs of angles. The 5, for instance, is between the 3-mark angle and the 2-mark angle. Therefore, it corresponds to the 3, which is also between the 2 and 3-mark angle. For the same reasoning, the x plus 3 corresponds to the 2x minus 8. So we write 5 over 3 equals x plus 3 over 2x minus 8, and we solve that to get x being 7. The length of AB then will be 7 plus 3, which is 10. And the length of BC will be 2 times 7 minus 8. That would be 2 times 7 is 14 minus 8 is 6. On problem number 19, we can find the length of AE by subtracting 8 minus 5. I've written it in there as 3. And now the little triangle on the inside, triangle AEB, is similar to the big triangle on the outside, again because we have corresponding angles congruent here by angle, angle. Therefore, forming ratios of corresponding parts, 3 is to 8 as x plus 2 is to x plus 8. Notice when we're doing 3 over 8, we're saying the left side of the small triangle divided by the left side of the big triangle, and when we say x plus 2 over x plus 8, that's the right side of the small triangle over the right side of the big triangle. We set those equal, cross multiply and solve, we get x equals 5/8. Plug those answers for x back in, and you'll find the lengths of AB and AC. The lengths of AB and AC then are 48 over 5 and 78 over 5 as shown. Okay, on number 20, again we're going to draw the two triangles separately. Triangle ABD has a right angle and an angle with 1 mark. Triangle FEC also has a right angle and an angle with 1 mark, so therefore they are similar by angle, angle. Again, forming ratios of corresponding sides, we set them equal. 3 over 8 equals x minus 1 over x plus 2, and we solve to get x equals 14/5. Plugging 14/5 back in for x, then BD is 9/5, and CE is 24 over 5. On number 21, the same process is used. Triangle ASR and ACB both have angles with one mark down at A, because they both share angle A, and they both have right angles. So they're similar by angle-angle. Forming ratios of corresponding sides, we find that x equals 8, which means that AS is 8 and AB is 15. Same idea again here. These two triangles are going to be similar by angle-angle. They both have the angles up at the top, which are congruent because the sun is shining down at the same angle on both the pyramid and on tallies there. And therefore, we'll take height over height. Actually, I took height of the pyramid over shadow of the pyramid equals tally's height over tally's shadow. That's an equivalent proportion. You may have written h over 2 equals 249 over 3, which is actually the way we've taught this. But after cross-multiplying, you'll have the same answer in either case. So the height of the pyramid is 166 paces, and since a pace is 3 feet, that's 498 feet. The surveying problem, number 43, I believe, is a little bit more involved here. There are 3 right triangles in the picture. Triangle OKM and POM both contain an angle with one mark, and which is the angle at M. I put one mark on it there, I guess, angle with one mark, and a right angle. Therefore, their third angles are congruent, and I put 2 marks on them, and importantly, the 2-mark angle is this angle P out across the river or stream on the other side. Okay, the third triangle then has the 2-mark angle, the right angle, and we could reason it has the 1-mark angle. Using triangle OKM and triangle PKO, since they're similar, we can form ratios of corresponding parts to find the length of PK and therefore the distance across the stream from K to P at 13.5 feet. Similar triangles are again used here. The triangles are similar because the light refracts at the same angle that it comes in, reflects at the same angle that it comes in. So the angles down where the mirror is laid are congruent to each other, and assuming that the man is standing at a right angle and the building is built as a right angle, we have 2 triangles that are similar by angle-angle. Forming ratios of corresponding sides, 1.92, the height of the man over the height of the tower equals the length along the ground from the man to the mirror over the length along the ground from the mirror to the building's base. Cross-multiplying and solving, the building is approximately 420 feet tall. In the next section on problems 14 and 15, we're using the triangle proportionality theorem. The triangle proportionality theorem says that if 2 triangles are, if you have a line that comes parallel to one side of a triangle, then it divides the other sides proportionally. Meaning, in this picture I'm drawing in the top left, that you could always set up the proportion A over B equals C over D. The parts of one side of the triangle are in the same ratio as the parts of the other. So on number 14, you see down over to the right, I've marked the information from 14 on the right side of our picture. You would have 4 over x, those are 2 segments of one side, are in the same ratio as 6 over 9, the 2 parts of the other side of the original triangle. We get x equals 6, and we can get our answer that xy is 10. The same exact process is done on the next figure here. The 8 that I've written in green there comes from taking 10 minus 2 for the length of segment my. So 2 over 8 is equal to t minus 2 over t plus 1. And again, we cross multiply and solve, and t is 3. On the next problem is the perfect setup for the proportionality theorem. X over 24 equals 3 over 18. We get x being 4, and AD, which is the length of x, is also 4. Again, a perfect setup for the proportionality theorem on number 17. 3 over 2x minus 3, the segments along one side are in the same ratio as the segments along the other side, 2 and 6. So again, I reduced the 2 over 6 to 1/3, crossed, multiplied, and solved. X is equal to 6. The length of ED then is 9. Number 18, again a perfect setup, so 16 over 20 is x minus 3 over x plus 5. We solve for x being 35 and plug it back in to find AC and CD's lengths at 32 and 40 respectively. Okay, we're going to have to use the theorem twice on number 19. First, we're going to use the segment BF being parallel to the bottom. That's the one that's easiest to see. So you would have 6 over x equals 8 over x plus 10/3. Solve that for x being 10. Now once you have that, you can work with the triangle, and this time now we're looking at the parallel line being segment FD there, and now we're going to say that y okay, I've erased a little bit there. Now using FE as the parallel line, we would have that DE, which is 2y minus 3, over CD, which is y, would have to equal FE, which I figured out using the value of x we just found, that FE has to be 40 over 3 divided by 8. Okay, well, if we cross multiply and solve here then, we have that 16y minus 24 equals, so 16y minus 24 equals 40y over 3. I elected at that point to multiply through by 3 to get rid of the fraction. So 48y minus 72 equals 40y. That would be 8y equals 72, and y equals 9. Y is the length of CD, so we know that CD is 9. And that leaves us only DE. And DE is 2 times 9, which is 18, minus 3 is 15. A very long problem, but just take each part as it comes. On number 33, to find x is really easy because, to find the y's is really easy because they're just marked equal. So 3y minus 9 equals 2y plus 6, and y is 15. The segment that is the length x plus 2 there is called a mid-segment, and because it's connecting the midpoints of two sides of a triangle. Therefore, we know it's parallel to the third side, and also its length is half the third side. Or put another way, to get the third side, multiply the mid-segment by 2. So 2 times x plus 2 is 5/3 x plus 11. Cross multiply and solve, and you get the value of x is 1. On number 43, it's explained pretty well there in print, but the idea here is because of those parallel lines will divide the segments along the road and the segments along the water proportionally. Now, another way to view this is that each lot to the total length has to be in the same ratio as its corresponding. For instance, the 20 corresponds with the length marked U. So 20 has the same ratio to the total frontage along the road as U does to the total frontage along the lake. Well, the total frontage is 113 along the road. The total frontage along the lake is given in the problem at 135.6. So, for instance, for the value of U, 20 over 113 is equal to U over 136. We solve each of those in the same manner, and we get the answers that are shown.